This lecture is on difference measurement. It corresponds to Chapter 4 of Foundations of Measurement, but of course there's a great deal more material in the chapter than I can possibly cover in this single lecture. The first thing to say about difference measurement, by way of introduction, is that conceptually we can think of it as being closely related to geometry. The two most fundamental notions of geometry, in fact, let's say the most important notion that one remembers, I think, casually from geometry, is that of congruence. And the simplest notion of congruence is that of congruence of line segments. Well, congruence of line segments just correspond to a comparison of line intervals. In that sense, axiomatizations of geometry that use intrinsically and in an important way the concept of congruence are closely related to what we want to cover in this lecture about difference measurement. That's a kind of historical background. Now, a characteristic feature of difference measurement, as we'll discuss it in this lecture, and as it's discussed in Chapter 4, is that we deal only with a one-dimensional case. We don't really deal with the geometry. That's a separate topic talked about in another lecture. So from a geometric standpoint, you might even say what we're doing in this lecture is not very interesting because it's one-dimensional. In that sense, it's like the real numbers. But it is, of course, exactly the case we're especially interested in measurement. Now, let's consider some examples. I mentioned congruence. What we want to talk about in terms of difference is a generalization of congruence in the sense that we want to talk about inequalities. So we want to say that one interval is larger than another. And it's important that we be able to say that. An example from psychophysics, a case of comparison of differences, is a person, for example, might be given two sounds and asked to find a third sound that just bisects the difference. That is, such that he's given sound A and C, and now he can adjust the apparatus to find B, such that he believes the difference between A and B is just the same as the difference between B and C. That'd be a characteristic use of the concept of difference. And that notion of bisection is widely used in a variety of psychophysical experiments. In the chapter, a number of related psychophysical methods are also discussed at the beginning of the chapter. An important application in other parts of the social sciences would be in economics to the notion of preference. And here a characteristic way of saying it is that in order to get cardinal utility, this is the way classically economists have talked, in order to get cardinal utility, we have to be able not only to order our preferences, but order our differences between preferences. So that, for example, if I prefer a novel of, say, Jane Austen is preferred to a novel of Norman Mailer, some particular novel, and I also say that I prefer a play by Sam Shepard is preferred to a play by you can put in your favorite dramatist there. Let me put in, say, Augie. Now what we would say is that in order to get a real sense of your preference and to have a cardinal utility, we have to ask for judgments. Well, do you prefer Austen? Is the difference between your preference for Austen over Mailer greater than your preference for Shepard over Augie? And such questions of difference are required in order to go on from an ordinal sense of utility, just an ordering, to a cardinal utility, which in terms of the theory of measurement means measurement up to fixing a unit and fixing a 0 point, that is, up to a linear transformation. Now, historically in economics, there's been objection to the kind of thing I just described, in the sense that you can't get direct behavioral evidence for the differences. You can get direct behavioral evidence in terms of the choices for the direct preferences, but not for the differences, the ordering of the differences. And it's been a subject of research to identify many different ways of observing, directly or indirectly, the differences in preference as well as the preferences. That's discussed some of the chapter and in many other places in the literature. I'll not review it here. It is important to be aware of the fact that there is a large and at times rather controversial literature about the way in which one is to get evidence from individuals about their differences, not just their preferences, but as it's sometimes put, about another way is about the intensity of their preferences. And this use of intensity here also is important to remark that in the classical measurement literature, difference measurement is often called intensive measurement, whereas what we have talked about in the previous lectures about extensive measurement is contrasted, and the difference that one has in mind historically, this distinction goes back a very long ways. In intensive measurement, you don't have any natural operation of combination, whereas in extensive measurement you do. And as we said at the introductory lecture in discussing some of the history, of course there are people in the past like Norman Cammell, who was in the earlier part of the century very influential in the foundations of measurement, both the theory and the philosophy of measurement, who claimed that in the case of intensive measurement there couldn't be any fundamental measurement. You couldn't start from scratch. Well, if Cammell had thought at all of and known very much geometry, he would have known how wrong that idea was. And the examples we give in this lecture illustrate also that in this classical sense, fundamental intensive measurement is certainly possible. It's important to note immediately that there is a close relation between having a difference representation and an additive representation. An additive representation is shown here if we have differences, algebraic differences. So we have the representation 5a minus 5b is equal to or greater than 5c minus 5d. Then immediately that's the same as saying in the additive representation 5a plus 5d is equal to or greater than 5c plus 5b. Now I mention that here because I won't return to this particular question in much detail, but what that shows is then that difference measurement is very closely related to conjoint measurement, where we have such an additive representation. And conjoint measurement is an important topic later on in this course and in the also in Foundations of Measurement book itself. I mentioned that there's this classical contrast between intensive and extensive measurement. It's interesting to note again, and I don't think Cammell was at all aware of Holder's important work of 1901, that in Holder's classical paper on measurement of 1901, there's already a reduction of the intensive or difference case to the extensive measurement. And the idea is very, very simple. Intuitively, you simply treat as an object the differences. And let's take these differences to be positive here. That'll be the simplest case. So a minus b is some positive, thinking of it in real numbers would be some positive real number. We can think of it abstractly as a certain object. And if a minus b is the same as b minus c, then we have a combination of a combined with a, which would be the same then in terms of thinking of these, the magnitude of the intervals as a minus c. So it's very clear how you can set that up, and Holder does that in a very well-defined and conceptual way, in a very clear mathematical way. So it's easy to reduce difference measurement in order to, for example, prove something or to show the relation to extensive measurement. Now, I've already remarked about some of these relations to congruence, and when we reflect on it and the various kinds of experiments that people are interested in, and the way they want to think about differences, there's sort of three obvious variations, and we'll discuss each of them in differing degrees of detail. First, we can simply have positive differences. And so this is very close to what I was saying about Holder. The interval AB is equal to or greater than the interval CD, and that's represented just by a function on the interval. Psi of AB, psi being a real-valued function into the positive reals, phi of AB equal to or greater than phi of CD. And here we may, I said positive because we might only permit, as we will initially, the formation of intervals when this is positive. So we don't have the interval AA. If we had AA, then that would be we would have psi also being non-negative. Now, those positive differences are a natural thing. A second thing, algebraic differences, the sort of thing I mentioned a minute ago. Here we do take account of the algebraic sign. And the third one, which is closest to congruence, in the case of congruence, it is exactly the absolute difference. In other words, we don't have naturally in geometry a direction that would give us algebraic difference. It's an important thing to note. The algebraic difference relation corresponds to having the natural ordering on the real numbers. But it's an important fact about, say, the geometry of the plane or any higher dimension, taking the Euclidean case, that no non-trivial binary relation can be defined. So in particular, we don't have any natural ordering relation. So we don't have, in the geometric case, the natural analog of algebraic differences. What we do have in the or in that sense, a natural analog of positive differences. What we do have in the geometric case is absolute differences. And it's this case of absolute difference that corresponds most closely to the way we think of congruence in geometry. And the only generalization here is, instead of simply taking equivalence, is to permit the inequality. It's rather interesting that it is so standard to take congruence in geometry. We forget how natural it is to take the slightly more general relation. In the case of different studies and the kind of applications in various experiments, etc., it's useful to have the inequality. Now, the program here is to discuss in decreasing scale these three cases. So we'll start with the positive difference case. And what we want to do is give axioms from which we can prove a standard representation theorem and uniqueness theorem. And so let's take a look at the axioms for positive difference. Now, first, in terms of the primitive concepts, we start with a non-empty set A of objects. Could be tones, depends on the application. Could be preference cases. There are any one of many different kinds of interpretations we would make in different sciences and for different experimental or empirical purposes. We then have a non-empty subset, A starred, of the Cartesian product of A with itself. Notice that this is a primitive concept because it's a non-empty subset. It's not the whole of the Cartesian product. Because, for example, we don't want the intervals that reflect negative differences. That is, if AB is positive, BA would be negative. We're not going to permit BA to be in A starred. We also aren't going to permit an A starred AA. That is the case that would be 0. And then we have the usual ordering relation on A starred. The axioms we want to look at a bit because they are like some of those in the case of extensive measurement, but naturally they have some characteristic differences because we have a different setup. For example, what is important to note here in terms of what I said earlier about intensive and extensive measurement, we don't have any operation here. We only have an ordering relation, but that ordering relation is sufficient. The first axiom is just that we have a weak ordering of A starred. And the second axiom, the rest of the axioms have a very simple meaning when we draw a picture. And the axioms look a little more complicated than they are because due to the fact that A star doesn't include all pairs, we always have to postulate the necessary pairs or an A star for the axiom to make sense. The second axiom, I guess I can draw the picture right here. That just says, if we think on the line, we have AB, and this will be positive in the line. It'd be simpler to draw that way. AB, and we have BC. Then we want to have the closure property. If AB is in A starred and BC is, then we want the closure property that the larger interval AC is in A starred. And the reason for that closure property on A starred is that we want to be able to have additivity. Intuitively, this axiom says that we have closure in A starred under addition of adjacent intervals. And it'd be a rather awkward mathematical structure if we didn't postulate that. The third axiom also says, using that same diagram, which we can draw here, that if we have A, B, and C, then if we look at AB and we look at BC, we would expect that the whole interval AC, the addition of AB and BC, must be strictly greater than either AB or BC. And notice the strict positivity of all of the intervals in A starred can be seen from axiom 3. Axiom 4 is a very natural additivity axiom in the same spirit. What this axiom says, if we have within A starred A, B, and C, and so we have A, B, and BC, and we also have the intervals A prime, B prime, and C prime. I've drawn it. I want to redraw it. I do it rather badly for the intuitive meaning. I want to make the intervals A, B, and C larger than the prime ones, A, B, and C. What this is now, if we compare AB and A prime, B prime, and AB is the unprimed interval is bigger. We compare BC with B prime, C prime, and the BC is bigger than B prime, C prime, then this whole interval AC is going to be greater than A prime, C prime. That's extremely intuitive. And so what we get from axiom 4 is a kind of monotonicity of ordering under a combination or a kind of additivity. Now axiom 5 is again a structural axiom that shows if we have a picture, let's draw a picture again, if we have AB and that's greater than, say, CD, and notice I'm making it positive to the left, easy to draw that way, keeping the left to right ordering the letters, then we can have a D prime such that AD prime, there exists such that AD prime is equivalent to CD. Historical remarks in order there. What that really corresponds to is the classical axiom in geometry for laying off segments. We're given a segment of given length CD. We have a segment array AB. Starting from A, we go to B. Then we can find the point D prime such that AD prime is equivalent to CD. So this axiom corresponds to that classical laying off of segments. And we also have that we can find another point, it's symmetric, D double prime, such that D double prime B is also equivalent to CD, which in terms of that laying off of segments mean we could have started at B and going toward A. We get that point D double prime. So that's very natural construction. It's not something, of course, that would always hold if we were given an arbitrary set A. We're postulating a structure on A that permits this axiom to be satisfied. In the kind of bisection experiment I mentioned earlier, we could certainly find that. For example, we could, in that case, get a special case of D prime equal to D double prime, or more generally, if we heard two tones, CD, we could find, and given A, we could find the D prime, such that AD prime is equivalent to CD, etc. Same thing about preferences. I could give many different empirical examples. The geometrical meaning, though, is perhaps the simplest to say in a very direct way. It's just like laying off of segments. And finally, we have a sixth axiom, which I haven't written down formally because it has a more or less standard form in terms of standard sequences. That's given on page 147 of the text, and is, of course, necessary and to get the desired representation. Let's turn now to the theorem we want to get, given these six axioms on a positive difference structure. What we assert is, as a representation theorem, there exists a real-valued function psi from mapping A starred into the positive reals, such that if AB and CD are an A starred, then AB is judged equal to or greater than CD as intervals, if and only if psi of AB equal to or greater than psi of CD. And secondly, we have the kind of additivity for adjacent intervals. If AB and BC are an A starred, then psi of AC is just equal to psi of AB plus psi of BC. You can see how close this representation is to what I was saying earlier about the Holder reduction to extensive measurement. The uniqueness part of the proof then, or the uniqueness theorem, rather, the uniqueness theorem asserts that psi is unique up to a racial scale, or up to a similarity transformation. Namely, if we have a psi prime with the same two properties, then there exists a real number alpha greater than 0, such that psi prime is equal to alpha psi. And second part now of the theorem that strengthens the structure, but is important in terms of getting a real valued function on the individual objects. Moreover, if for every A and B in A, that is the original set of objects A, and A not equal to B, we either have AB or BA in A starred. So it means that A starred is now a complete ordering and not a partial ordering. Then there exists a real valued function phi from A, not A starred, from A into the reals, such that psi of AB equals phi of A minus phi of B. And secondly, relative to this psi, if we have any other such phi prime, then that must be equal to phi plus beta. Beta, of course, being a translation parameter. And this is what we'd expect. But notice, of course, that as in the case of the geometry, when we get to the objects themselves, not the length of the intervals, but the objects themselves, we don't have a natural origin. That's reflected in beta here. That's what we mean by having an interval scale. All right, now let's take a look at the proof of this theorem. The first place we want to simply, as I said, follow Holder's idea. Now the first thing we have to look at in carrying through that idea technically is that if I had an interval AB and one CD, I can't concatenate them where they aren't adjacent. Well, there's an obvious move we make in the theory of measurement, and it's a characteristic move, and one we use here. We form equivalence classes, and then we can concatenate the equivalence classes arbitrarily because we can be assured there's an appropriate concrete representation to carry out the operation. So we form the equivalence class, given any interval AB, we form the equivalence class AB. I've shown that here by underlining in the text. It's printed in boldface. The equivalence class AB is the set of all intervals CD and A starred such that CD is equivalent to AB. Then we want to form the set B, which is the set of all intervals in A starred underline. That is the set of all these intervals. And there exists AB such that AB is in gamma and BC is in delta. That is, there exists AB and BC in the original set A such that AB is in gamma, BC is in delta. So, in other words, B is just the carrying of the pairs up to the equivalence classes. That is a comparison of intervals. And then the operation O is a mapping of B into A starred. So we combine these pairs to go into A starred. Now notice something, so we're to be clear about it. B is itself not the ordering relation at the equivalence class level. We postulate we have the equivalent, we bring that equivalence class relation up in the standard way, printing it in boldface or underlining it as we wish. B is a set of equivalence classes of intervals, pairs of equivalence classes of intervals. We need this in order to get the exact structure for the representation we want, to reduce this to one of the standard cases we would use, for example, in extensive measurement. Before we say that, let's look at this simple lemma that if we have gamma O delta equals AC, and notice gamma now is an equivalence class of intervals, delta is an equivalence class of intervals, and by the way we defined it here, we have this concatenation. Then there exists a B and A that just gives us AB equal gamma and BC equal delta. And that's obvious from the construction. We can show that's always the case using axiom 5, the one I just discussed, the axiom I like to call the one corresponding geometrically to the laying off of segments. All right, now what we want to show in the basic proof that'll get us the function psi, the real valued function psi, is now to take this structure we've defined, A starred, the ordering on A starred equivalence classes, and the ordering, which I would put boldface like that, B and the concatenation. That structure we want to show is just an Archimedean, regular, positive, ordered local semigroup. Now that's just definition 2.2. And if you go back to 2.2, that's in chapter 2, definition 2, there are 8 axioms that we need to satisfy. And we'll make a quick review of those axioms. We can show that this structure we so constructed, by using the axioms directly on positive differences, will satisfy the axioms for this local semigroup, which will then give us immediately the representation, psi. First, we have to have a simple order. Well, as a characteristic move, when we take equivalence classes and we start with a weak order, we get a simple order under the equivalence class structure. So that's direct to satisfy axiom 1. Axiom 2 is that we want a monotone closure of B, which says is that if we have gamma delta in B, gamma is greater than gamma prime, delta greater than delta prime, then gamma prime delta prime must be in B. And that's easy to construct from the axioms we've got for positive difference. I won't, maybe I'll say something about it. Let's take the case where gamma equals AB, and where gamma is equivalent to gamma prime, there's no problem. Let's take gamma strictly greater than gamma prime. So we choose a B prime, which we can, such that AB prime, B prime B is an A starred. And AB prime is equal to gamma prime. Essentially, we're using axiom 5. So the picture looks like this. We have AB and BC. Now we can choose this B prime. But once we've chosen that B prime, it's easy to show, as the picture shows, that B prime C is at least as great, B prime C is at least as great as BC as an interval. Then we can choose C prime such that B prime C prime is equal to delta prime, and so we have gamma prime delta prime in B. Axiom 3 and 4 for these local semigroups, monotonicity, and that follows immediately from axiom 4. Remember, axiom 4 is a kind of monotonicity under addition of intervals of the ordering relation. Addition, I should say, of adjacent intervals. So that comes from axiom 4, which I drew a picture. Here's the axiom, and there's the picture. Remember, we have AB greater than A prime B prime, BC greater than B prime C prime, then AC greater than A prime C prime. Axiom 5 is to show that the operation of concatenation we defined is associative. That's straightforward, and I won't say much more about it. Easy to show from the construction. Positivity, well, we already have positivity of the intervals from looking directly at axiom 3, namely that any interval that we get from 3 easily, every interval is positive. And regularity, again, regularity means here the postulating of the kind of objects to give us these equivalences we get with D prime and D double prime. So regularity, which is axiom 7, comes directly from axiom 5 for positive differences. And finally, axiom 8, which I haven't written down here, is of course the standard Archimedean axiom for the local semigroups, and we can show that the Archimedean axiom for positive differences gives us, in the structure of this local semigroup, a satisfaction of that axiom. So what we've done, and it's a characteristic move always when we can do it, we reduce one of these proofs. Instead of starting from scratch, we reduce one to something already proved, as we've done here. Having done that, it then follows at once that the function psi we posited, remember psi is a real valued function that preserves the order on the intervals and has this property of addition of adjacent intervals. Such a function psi then exists immediately from the known theorem for the local semigroup satisfying definition 2.2. The next thing now we want to look at very quickly to finish this is the construction of the function phi. Let's turn to that. So to finish the proof, we define phi in terms of psi as follows. We pick an a sub 0 that intuitively will have the assignment of the number 0 to it. So phi of a equals psi of a0, that is the interval a to a0, if a0 is positive, that is an a starred. Phi of a is 0 if, of course, a is identical to a0, and phi of a is minus, or the negative of the value of psi of a0 if a0a is positive, that is a0a is an a starred. And then it's straightforward to show, as it's done in detail in the chapter, that phi of a has the expected properties. Let's now turn to the second case of differences, the case of algebraic differences. Here the primitives are simpler because we have the relation hold for all pairs. So we just have a non-empty set A and then an ordering relation on the Cartesian product of A with itself. The axioms are also simpler because we don't have to guarantee this being an A starred that we had in the case of positive differences. The axioms of the three cases discussed in detail in the chapter, positive structures, algebraic differences, and absolute differences, the axioms certainly are the simplest for the algebraic differences. The first axiom is, as before, just the weak ordering of the pairs, that is, of the differences, the algebraic differences, under the binary relation, the familiar axiom. The second axiom catches the essential algebraic character, namely, if the interval AB is equal to or greater than CD, then DC is equal to or greater than BA. And notice how simple that is algebraically. So algebraically, we have A minus B equal to or greater than C minus D. Then we have immediately that D minus C is equal to or greater than B minus A. Just multiplying through by -1 and reversing the inequality in the familiar fashion. So that's just the meaning of axiom 2. Axiom 3, well, that's just our monotonicity axiom for positive differences that we discussed earlier in the same form. If AB, the interval AB, is at least as great as A prime B prime, and BC is at least as great as B prime C prime, then putting AB and BC together, we get an interval AC, which is at least as great or greater than A prime C prime. And axiom 4 is just the regularity axiom we had for positive differences with the obvious minor changes. If we have AB interval is at least as great as CD, which is at least as great as the null interval, AA, then we have D prime, D double prime, such that we can find AD prime equivalent to CD equivalent to D prime B. And I drew a picture for that in discussing positive differences. And finally, axiom 5, we have the Archimedean axiom that I'm not stating explicitly. But notice we just have 5 axioms here, and they have a very simple form. I might say these axioms result from several that have been given in the literature, the history of the various axioms for algebraic differences is stated, and this represents, I think, essentially about as simple a set of axioms as we can expect to get for the general case. Now, the representation theorem is then slightly different. We want to go directly. We don't have a function psi. We want to go directly to a phi on the individuals in A, individual objects. So there exists a real valued function phi on A such that the interval AB is equal to or greater than CD if and only if phi of A minus phi B equal to or greater than phi C minus phi of D. That's the change we'd expect for algebraic differences. The uniqueness, phi is unique up to a positive linear transformation. That is, the 0 point is arbitrary and the unit is arbitrary. Now the proof of this representation theorem, once we have the proof for positive differences, is very straightforward. The idea is completely simple. The complete details are given in the chapter. Let's be clear about the idea. We reduce an algebraic difference structure to a positive difference structure and show then the axioms for positive difference structures are satisfied in this reduced version. So we want to define first A starred. AB is an A starred if and only if AB is strictly greater than AA, the null interval. And we restrict the ordering relation to the ordering relation starred is just the restriction of the ordering relation for algebraic differences to A starred. And then we define a set of equivalent objects. A, B are equivalent. Well, formally we can put it neither AB nor BA is an A starred. Intuitively it just means that in the ordering A is equivalent to B, where we now define in the natural way for algebraic differences from the weak ordering for the differences we define in a natural way using this null interval. We define the ordering on objects. So that's intuitively the content of E. And then we just have these E equivalence classes, and we prove in a direct way that we have satisfaction for these E equivalence classes of the positive difference structures using A starred as shown. And I won't walk through the details of that. It's very similar to what we've already discussed for positive difference structures. The reduction is intuitively quite straightforward. There is an important point, not only a mathematical point about the representation, but one that is sometimes of concern in applications. Namely, we can have alternative numerical representations. Remember, as we emphasize in the discussion of the various representation theorems, the exact form of the numerical representation is not God-given. There are alternative choices, and there's nothing in the mathematical structures themselves, these alternative structures for numerical representation, that dictate a choice to us. It's a matter of convenience, what fits in with the theoretical setting they're going to be used, and so forth. So we can, in the case of algebraic differences, if we define a function psi, now this psi has nothing to do with the psi function I defined in proving the representation theorem for positive differences. This is a new psi. If psi is defined as e to phi, then psi in this form is a racial representation. And this familiar exponential relation here between psi and phi is a way of going from the difference representation to the ratio. And obviously you can go from the ratio to the phi by taking logarithms. And the racial representation has in this kind of formulation where the interval AB is at least as great as CD if and only if the ratio phi of A to phi of B is equal to or greater than phi of C to phi of D. And of course, phi and psi aren't at all linear transformations of each other. That's obviously being exponential. And I want to come back to that now by considering an elementary special case that puts in particularly interesting focus how we think about phi and psi. And that's the case where we don't satisfy the general axioms here, but we have a weaker structure for algebraic differences that has some applications. It's been used, was used, for example, more than 20 years ago by my colleagues and myself in some experiments on utility differences. That is, when we go to finite structure of algebraic differences, but we have equal spacing. So we think of the objects as being spaced in the ordering this way. So intuitively, this interval, each atomic interval, is equal to every other. Now, to formally express this equality of atomic intervals, we have this notion of a successor relation J. B is the successor of J if and only if AB strictly greater than AA, that is the null relation, and it is not the case there exists a C such that AB is strictly greater than AC, greater than null. That is, you can't find, if you have A and we have B here, we can't find a C in between. So the way to read that is A precedes B in the ordering, immediately precedes, or B is the immediate successor of A. We'll see how we use that axiom. All right, now our axioms, the first three axioms are just what we had before. We have a weak order, we have a finite set A now in the same ordering relation. Axiom 2 is just as I discussed earlier. Axiom 3 is just as I discussed earlier. Let's remember what 2 and 3 are. Axiom 2 is just algebraic axiom. If AB at least as great as CD, then reversing sign, DC is at least as great as BA. And axiom 3, the monotonicity axiom. So we have those three simple axioms: weak order, algebraic sign, monotonicity. And we just add one more axiom. If A is the immediate predecessor of B and C is the immediate predecessor of D, then the interval AB is equivalent to CD. So, for example, draw out a picture. If we have A here and B here as an atomic interval, and D is an atomic interval, that C is the immediate predecessor of D, then we say that these two intervals must be equivalent. So that equal spacing is a particularly simple structure. And we can get immediately from these four axioms, everything, as you'll notice, is totally elementary. Because of the finiteness, no Archimedean axiom is needed. We can get a similar representation of a function phi, unique up to linear transformation. Now, interesting question, which way do we want to represent those equal differences? In terms of ratios or in terms of differences? And I think our choice, and we see it particularly vividly here in this very simple equal spacing structure, our choice as to whether to have a difference representation, a numerical difference or a numerical ratio, will depend on the framework of application. And I might say probably as much as anything, if we're dealing in an area where there isn't an extensive theoretical development, then it'll be chosen, that is, the representation as a difference structure or as a ratio structure will be chosen depending on what the history of usage has been in this particular area of study, as, for example, in many cases in psychophysics. Now, the third case of differences, the case of absolute differences, I won't state the axioms because the axioms, the flavor of the axioms are similar. There have to be technical differences. An interesting aspect of the axioms that are given in the chapter for absolute difference is that only the Cartesian product of A itself and the relation is required. And in the earlier discussions, for example, by Holder and in early axiomatization by myself and Winnett, we also, because of having absolute differences, we also added an ordering relation on A. So, and it was shown by Kramps and Tversky that this ordering on A is not needed, that you can construct, if you're a little clever about it, you can construct from this ordering of the absolute differences an ordering on A cross from the ordering on A cross A, we can construct a difference, an ordering on A itself. And the details of that are gone through rather carefully in the chapter, and I won't discuss that and the resulting axioms in this lecture. I think in many ways, when you look at the various axioms, it's quite clear that the nicest axioms in the sense as an axiomatic structure are those for algebraic differences. But in many applications, we're really interested in either positive differences or absolute differences. Moreover, as remarked, absolute differences are the different structures that correspond to the classical case of congruence, and also they're close to the idea of distance for an arbitrary metric space. So that from a geometrical standpoint, even though the axioms are more complicated, the absolute differences represent the natural concept.